picture this scenario for a second, right? You're a drone.
Right. A highly expensive piece of military hardware.
Exactly. You're flying, let's say, a couple hundred kilometers behind enemy lines. The mission is critical, the target is locked, and the air is just perfectly quiet.
Smooth sailing.
Yeah, but then, without any warning at all, the sky just fills with these invisible, totally impenetrable walls of electromagnetic noise.
Just absolute chaos in the radio spectrum.
Right. And your remote control link, the one connecting you to the human operator, it's instantly dead. Your GPS, that invisible grid telling you where you are, gone.
Completely jammed out.
Yeah, satellite feeds are dead. Now, for most machines in aviation history, I mean, from old biplanes right up to modern fighters, losing all that spatial awareness is basically the end of the line.
Oh, absolutely. The fail-safes kick in, or they just drop out of the sky.
Or they just wander aimlessly until the batteries die, you know. But this specific machine we're talking about today, it doesn't blink. It doesn't panic. The exact millisecond that signal dies, it stops being a remote-controlled tool.
It just starts thinking for itself.
Yes. And welcome to today's deep dive, everyone. We are jumping into this completely fascinating and, honestly, kind of terrifying collection of source materials today.
Yeah, it's a massive stack. We've got military technical reports, academic journals.
Engineering white papers.
Right, and strategic analyses,
Yes.
all detailing this incredible high-tech cat-and-mouse game playing out right now.
And our mission today is to really unpack this one specific section of the documents. It's labeled the key core technologies.
Section 8 in our source stack, yeah.
Section 8. And this details the underlying hardware and software, keeping these autonomous systems alive in, frankly, the most hostile electromagnetic environments on Earth.
We are looking at the absolute bleeding edge here. Edge computing, visual navigation, electronic survival.
Even the physical manufacturing processes.
Exactly, how you actually build a machine that can do this.
And if you're listening and thinking like, hey, I'm not a military engineer, I work in sales, or, I'm just driving to work, why do I care?
Yeah.
Let me just stop you there.
Because it applies to everything.
Right. What we are talking about is the absolute limit of autonomous robotics. The tech being forged in this crazy high-stakes environment is exactly what's going to dictate the commercial world soon.
It's the blueprint for the next decade.
Yeah, autonomous vehicles, delivery networks, supply chains. I mean, the math these engineers are inventing to keep a drone from crashing when its GPS is hacked.
It's the exact same code that'll keep your autonomous family car on the road during a network outage.
Or a solar flare, yeah.
Right.
So before we even talk about how these things hunt, we have to talk about how they just survive the trip.
Yes.
We have to completely let go of this idea of human control.
Right. The military actually calls this the man-out-of-the-loop era.
Man out of the loop. I love that term, but it's also a bit scary.
It is. And to really grasp it, you have to understand the invisible war happening first. The sources talk about these layers of systems designed to just blind and deafen anything in the sky.
Like the Krasuka 4 system.
Yeah.
Right?
Exactly. The Krasuka 4. And this isn't just some guy pointing a jammer like a flashlight. This is a massive ground installation. It creates this huge bubble of broadband interference.
A 200-kilometer radius, the report said.
Right. So imagine an entire major metropolitan area, plus the suburbs, just blacked out in the radio spectrum.
Just blasted with static.
Yeah, the sheer wattage just fries delicate receivers. It disrupts low-orbit satellites, blinds airborne radar, and it definitely cuts the link between a drone and the pilot.
But the Krasuka is just brute force.
Yeah.
The reports also mentioned these more, I guess, sneaky systems.
The tactical ones, yeah, like the Stora jammers.
Right, which sweep noise specifically to kill video feeds. And then there's the Lima system, which this one blew my mind.
Yeah. Lima is nasty. It doesn't just jam GPS, it spoofs it.
Spoofs it. So instead of just screaming over the satellite so the drone can't hear, it basically impersonates the satellite, right? It feeds the drone a lie.
Exactly. It broadcasts fake satellite ephemeris data. That's the precise orbital mass the satellite sends down, and it messes with the timestamps.
Because timing is everything for GPS.
Right. And because the Lima system is on the ground, it's way closer to the drone than a satellite 20,000 kilometers in space. So its fake signal is much stronger.
So the drone's receivers are just like, oh, strong signal, let me lock onto that.
Exactly. And suddenly the flight computer does the fake math and says, oh, wow, I am currently 500 meters underground.
Or like, I'm flying completely upside down over the ocean.
Right. And if the automated systems believe that lie, they try to correct the flight path aggressively.
It pitches down to fix an altitude error that doesn't exist and just boom, drives itself into the concrete.
A fatal, unrecoverable error.
Yeah.
Which is why the man-out-of-the-loop thing is a necessity now. Relying on an umbilical cord, whether it's a pilot with a joystick or a GPS satellite, it's just not viable anymore.
The second that cord is cut, it has to become fully autonomous. But here's my thing. Running AI, like real decision-making neural networks, that requires massive computing power.
Massive power and massive cooling.
Right. We've all seen those huge liquid-cooled server racks for AI. You can't just strap 100 pounds of servers to a tiny battery-powered drone.
Which is where Section 8's hardware engineering is just wild. They outline this custom-built dual-board system called the JetCore FC.
JetCore FC?
Yeah. It physically separates the flight systems from the AI brain. So you have this highly reliable flight controller and STM32H7 microcontroller.
That's the part doing the basic flying, right?
Exactly. Aerodynamics, motor timing, basic safety. And that is paired with a dedicated AI platform, specifically a heavily modified NVIDIA Jetson Orin chip.
Wait, I know NVIDIA chips. The ones running major AI models are huge. They generate enough heat to literally fry an egg? How do they shrink that to fit on a drone without melting the chassis?
Extreme optimization. I mean, the whole JetCore FC core board is only 136 by 66 millimeters.
So roughly the size of my smartphone.
Basically, yeah. And the total weight for both boards is 55 grams.
Hold on, 55 grams. That's lighter than a tennis ball.
It really is.
You are telling me they fit an AI brain that replaces a human combat pilot onto something lighter than a tennis ball?
Yes, and it's heavily ruggedized, too. The reports highlight the use of military-grade conformal coatings.
Conformal coatings, what exactly is that?
It's these specialized microscopic polymer films they apply directly over the circuitry. It seals it completely.
So it protects it from water and dust.
Moisture, chemical dust, and massive temperature swings. This 55-gram board is rated to operate from negative 40 degrees Celsius up to positive 85 degrees Celsius.
That is insane. And how much math can this tennis ball actually do?
The Jetson Orin module pushes up to 100 TOPS. That's tera operations per second.
100 trillion operations a second. Wow. But wait, I noticed the report said it's running INT8 deep learning. I thought big AI models needed 32-bit floating point math for all those precise decimal points.
Usually, yes.
So doesn't downgrading to INT8 make the AI kind of dumb?
It's a trade-off. It sacrifices a rate. Since it can't ask a satellite where it is, it figures it out by feeling its own momentum and looking at the ground. It fuses two distinct data sources. First is the MEMS IMU.
The microelectromechanical system's inertial measurement unit. Basically, the drone's inner ear.
That's a great analogy.
Yeah, like how human fluid in our ears tells us if we're falling or leaning. The IMU is just a tiny silicon version of that, right?
Exactly. It measures acceleration, pitch, yaw. It gives hundreds of updates a second about how it's moving through space. But these tiny MEMS IMUs have a flaw: they drift.
Right, tiny calculation errors.
Yeah, fractions of a millimeter of error. But over a few minutes, those errors accumulate, and the internal map drifts wildly away from reality.
Like if I put a blindfold on and tried to walk a straight mile using just my inner ear, I'd end up walking in a huge circle.
Exactly. So to fix the drift, it uses the second data source, its eyes, the camera. As it flies, the JetCore board runs an algorithm called ORB on the video feed.
ORB. I'm guessing that means it's not looking at the whole HD picture, just looking for landmarks.
You got it. Processing every pixel takes too long. ORB stands for feature points, high contrast corners, right angles of a building, a road intersection.
Oh, like navigating a dark room by just looking for the glowing exit sign.
Perfect comparison. It tracks how those mathematical feature points move across the sensor from one frame to the next. By measuring that pixel displacement over, say, 1/10 of a second, it knows its exact relative speed.
So the inner ear feels the momentum, and the eyes confirm the actual distance moved. But how do those two completely different types of data actually talk to each other?
That's the math magic. They use an extended Kalman filter, noted as EKF2 or EKF3 in the report.
A Kalman filter.
Yeah, it's a statistical loop, predict and update. The filter uses the inner ear to predict where it should be next millisecond. Based on my speed, I move 2 meters forward.
But it knows the inner ear drifts, so it can't trust it totally.
Right. So it takes the visual data from the ORB algorithm, the measurement, and compares it against the prediction. It calculates the error margin and updates its true position.
So the eyes correct the drift, and the inner ear fills in the microsecond gaps between camera frames. That is an incredibly elegant loop.
It is, and the reports show this AI-enhanced VIO keeps long-distance drift under 1.5% of the total flight distance. It can fly for kilometers with zero GPS and know exactly how far it went.
Okay, but here's the flaw I see. What if the camera can't see? If it's flying over a battlefield, there's going to be smoke or fog.
Yeah.
If it can't see the ground, the ORB algorithm can't find those sharp corners.
And that is the critical vulnerability of traditional VIO. In degraded environments, smoke, dust, or even flat, featureless water, the geometric corners vanish. The filter loses its data, and the tracking success plummets to zero.
So if I can't see my feet, my eyes can't help my balance.
Exactly. But Section 8 details a massive leap to solve this. Deep Patch Visual Odometry, DPVO.
Whenever I hear deep in these tech reports, it usually means neural networks are taking over.
They absolutely are. DPVO drops the search for sharp geometric corners and uses convolutional neural networks, or CNNs.
Okay, so how does a CNN see differently?
Instead of looking for a sharp line of contrast, it looks at patches of pixels. That's the deep patch. It learns to track subtle textures and gradients that don't disappear when the lighting changes or if there's smoke.
So it's using like a mathematical peripheral vision. Even if the building corner is blurry from smoke, the AI tracks the general blurry texture to keep calculating speed.
Exactly. It turns the obstacle into part of the navigation. The data shows that even in severe haze where traditional algorithms instantly fail, the DPVO network keeps an 86.1% tracking success rate.
And it does that on INT8 math on a 55-gram chip.
Which is just staggering engineering.
Okay, so the drone knows how it's moving relative to its starting point. It knows it hasn't crashed. But relative movement isn't absolute coordinates. If the GPS is dead, how does it know where on the planet North actually is?
Right. VIO keeps you flying straight, but it doesn't give you a global map position. That brings us to terrain reference navigation, specifically the problem of low-altitude flight.
Because if you're at 30,000 feet, you just take a picture straight down and match it to Google Earth, basically.
High-altitude optical map matching, yeah. But in electronic warfare, flying high gets you shot down instantly by radar. You have to fly low, below 25 meters, hugging the terrain.
And when you drop that low,
you hit what engineers call the viewpoint distortion flaw.
The viewpoint distortion flaw. I love this concept. If you're listening, imagine trying to walk down a city street, but your only map is a satellite photo of rooftops.
Right.
What you see from the sidewalk, the storefronts, fire hydrants, looks absolutely nothing like the flat, top-down satellite view.
The perspective is totally warped. At 25 meters, a 2D satellite map is useless. The drone's camera sees the side of a tree line or a concrete wall. That doesn't match the flat pixels of a map.
So how do you fix a map you're looking at from the wrong angle?
You stop looking at 2D pictures, you shift to 3D shapes. They use height map matching driven by something called a particle filter.
Particle filters and height maps. Let's break that down. How does it know the height of the world?
Before launch, they load a digital elevation model, or DEM, into the drone. No color data, no photos. Just a 3D topographical map of exact physical heights, hills, valleys, buildings.
Okay.
As it flies, sensors like a stereoscopic camera or solid-state LiDAR capture the actual 3D structural topology around it in real time.
So it's physically feeling the shape of the world, like reading Braille, rather than looking at colors.
Yes. Now, the particle filter, since it doesn't have GPS, it generates thousands of particles. Each particle is a mathematical guess of where the drone might be on that 3D map.
I picture this like waking up in a pitch-black room in your house. You know the layout, but you don't know which room you're in.
Exactly.
So you reach out, feel a smooth surface at waist height, and guess, okay, I might be at the kitchen island. You step forward, hit something soft, and realize, nope, bumped into the couch, I'm in the living room. You eliminate the wrong guesses until you know exactly where you are.
That is a perfect visualization. The computer compares the 3D shape it's feeling right now against what the map says should be at each of those guessed locations.
And as it flies forward at 100 kilometers an hour, it's getting massive amounts of new 3D Braille to check.
Right. And any guess that doesn't match the physical terrain is instantly discarded. The raw particles die off, and the remaining ones mathematically cluster onto the single most probable location.
Completely bypassing the viewpoint distortion flaw. It doesn't matter if the building is painted differently or hidden in shadows.
The physical height of the concrete perfectly matches the map. And once those particles converge, the algorithm outputs standard military grid reference system coordinates, MGRS, right into the flight controller.
Pinpoint absolute position without a single GPS ping. That is incredible. And this ties back to what we said earlier. This military tech is already bleeding into civilian regulations,
Yes, the reports specifically reference civilian ASTM F3422 standards.
which is the framework for detecting near-mid-air collisions in commercial airspace.
Exactly. For the FAA to let delivery drones fly beyond visual line of sight, they have to mathematically prove the drone won't just crash into a skyscraper if the cellular network drops.
Right, we lost signal. Isn't a good excuse when you're delivering blood to a downtown hospital.
So this highly robust 3D height map navigation, tested in deliberate electronic warfare, is exactly what will let civilian fleets navigate our cities safely.
It's the ultimate stress test. Okay, let's move the timeline forward. The drone survived the jamming. It navigated the 3D maze. It's at the target grid.
Yeah.
But here is the next massive hurdle from Section 8. The target knows it's being hunted, and it's hiding.
Right.
How does a machine know what to strike when humans are actively trying to trick its eyes?
Now we shift from navigation to automatic target recognition, or ATR. The human is still completely disconnected. That NVIDIA Jetson Orin chip dynamically shifts its computing power. It stops navigating the terrain and runs a heavily pruned TensorRT neural network dedicated entirely to finding the target.
Heavily pruned. I want to dig into that. I think of a neural network as this massive, interconnected digital brain. What does it mean to prune it? Do they just delete code?
Kind of. When you train a huge model on a supercomputer, it builds millions of parameters, synthetic synapses. But a lot of those pathways are barely used. Pruning is the math process of finding those weak connections and severing them, cutting the dead weight.
Shrinking the model so it runs lightning fast on that 55-gram board.
Exactly. Because in a terminal attack dive, it doesn't have time to ponder. It has to run inference, making a definitive decision on unseen data multiple times a second with zero latency.
So it's scanning the video feed, hunting for geometric signatures.
Right. The turret of a tank, the dish of an air defense radar. When it finds a pixel cluster that matches, it draws a digital bounding box around it.
Like the little yellow squares on your smartphone camera when it sees a face.
Conceptually identical, but with a kinetic warhead attached. The second that box is drawn, the ATR system generates virtual tracking anchors. It locks onto those pixels, bypasses the navigation, and physically takes over the flight controls to dive straight at the bounding box.
Fully autonomous engagement. But humans aren't just sitting there passively. The sources detail these bizarre, almost archaic countermeasures against this AI.
Oh, it's a fascinating evolution. Ground forces realize these AI models are trained on standard military camouflage geometry. So to break the math, they literally started painting multi-million-dollar armored vehicles with high-contrast black and white zebra stripes.
Zebra stripes on a tank. I saw the photos in the appendix. It looks completely absurd.
To a human eye, a zebra-striped tank in a green forest is a neon sign. But the AI isn't looking at the forest. It's hunting for the straight edges of a steel chassis. The stark contrast of the zebra stripes creates massive geometric distortion in the digital image.
So the neural network's edge detection just fails. It sees fragmented shapes instead of a cohesive vehicle.
Exactly. The confidence score drops, the bounding box breaks, and the drone flies right past it.
But couldn't engineers just retrain the AI, feed it thousands of pictures of zebra stripes and say, hey, a zebra in a pine forest is a tank?
You could. But next week, the enemy changes to digital polka dots. Or they throw an asymmetrical tarp over it. If you rely just on visible light and geometry, you're always playing catch-up, which is why they developed the countermeasure, decamouflage.
Decamouflage. How do you teach a machine to mathematically ignore paint?
By using a different spectrum of physics, dual verification. They pair the optical camera with a high-resolution thermal imaging sensor.
Right, because a tank isn't just a box, it's a 1,500-degree metal engine block.
Precisely. You can paint the armor however you want, but you cannot hide the inevitable thermodynamic heat contour of a 1,000-horsepower diesel engine.
The glowing exhaust, the friction of the steel tracks.
The decamouflage algorithm cross-references the visible geometry with the thermal map in real time. Even if the optical camera is confused by zebra stripes, the thermal camera overrides it. I don't care what color it is, it has the exact heat signature of a T-72 engine block.
The AI dynamically weights the thermal data. That proves a fundamental rule here. You can trick a lens, but you can't hide from thermodynamics. But what if they fake the thermodynamics? The sources mention an entire strategy of decoys and saturation.
Right. If you can't hide, you overwhelm it. You give the AI too many real-looking targets to process, forcing it to waste its kinetic energy on garbage. They use Gerbera-class decoys, basic wood, or polystyrene foam drones that cost around $10,000.
Now, $10,000 sounds like a lot for a foam plane, but compared to a $2 million interceptor missile, it's pocket change.
It's a rounding error. And they aren't just empty gliders. To make them cheaply and quickly, they use SLS selective laser sintering, an industrial 3D printing technique along with basic thermoplastic composites to print internal radar reflectors.
So the 3D printed shapes inside bounce radio waves back, making a small foam drone look like a massive loitering munition on radar.
Exactly. And they strap cheap heat emitters to the tail so they look like a real combat engine on a thermal camera.
So the strategy is a massive saturation attack. Launch dozens of wooden fakes right alongside the real drones.
The enemy radar sees a massive incoming swarm. The defender's AI can't distinguish between a $10,000 foam decoy and a real threat. They look mathematically identical.
Which forces a terrible choice. They had to turn their radars on, exposing their location, and fire million-dollar missiles at wooden fakes.
Rapidly exhausting their ammunition. Once the batteries are empty, the real autonomous drones trailing behind slip through and strike the defenseless radar sites. It's severe economic attrition.
Okay, so we're deep into futuristic cyber warfare. But here's where this deep dive takes a wildly unexpected turn. Because one of the most effective solutions to bypass all this electronic warfare is literally 19th century technology.
It's a stunning pivot. When the airspace is so saturated with jamming that no radio wave survives, and it's too chaotic for DPVO to navigate safely, they abandon the wireless spectrum entirely. They built the fiber optic drone.
Instead of an antenna, it just carries a massive spool of literal wire.
A spool of ultra-thin glass or polymer fiber optic cable. As it flies, it physically unspools this continuous thread behind it, connecting it directly back to the operator.
I am marveling at the steampunk nature of this. An AI robot soaring over a modern battlefield, trailing up to 65 kilometers of string. It's the world's deadliest kite.
It sounds archaic, but the advantages are absolute. Communication happens via microscopic pulses of light down a shielded glass tube, 100% electromagnetic immunity.
You can't jam a piece of physical glass with a radio wave.
You cannot. The whole 200-kilometer Krasuka 4 array can point at it and it does nothing. Plus, zero RF signature. It's radio silent. Enemy sensors can't detect it, and they can't trace a signal back to drop artillery on the human pilot.
And since it's fiber optic, the internet stuff, the data rate must be huge.
Unjammable, zero latency, uncompressed 4K video directly to the operator's goggles. The pilot manually flies into tight spaces, totally ignoring the electronic chaos.
But the engineering to make a 65-kilometer string fly without snapping.
Yeah.
Let's start with the economics, because this ties into the civilian AI boom. The economic war over raw materials is fascinating. You need incredibly thin, lightweight, bend-resistant fiber. The industry standard is G.657.A2 single-mode optical fiber. And the military isn't the only one who wants it.
No, that exact grade of fiber is needed to wire the massive new AI data centers being built worldwide. The explosive demand for commercial AI has created a massive bottleneck.
The drone makers are in a bidding war with tech giants.
Right. The cost of a 50-kilometer spool jumped from $300 to over $2,500 almost overnight.
Wild. But moving from economics to physics, there's a massive problem with putting a high explosive inside a tightly wound ball of string.
Mechanical engineering gets complex here. To maintain the center of gravity, they initially put the explosive charge inside the hollow core of the fiber spool.
Makes sense on paper.
Until you detonate it. The massive ring of tightly wound fiber actually acted as a physical shock absorber.
The communication wire dampened the bomb.
Like dozens of layers of Kevlar, it absorbed the kinetic energy, reducing the speed of shrapnel and shrinking the lethal radius.
So how do they fix it? You can't just move a 10-pound spool to the back. It won't fly straight.
They redesigned the internal chassis. They invented fragmentation shielding. They used those advanced materials from Section 8, specifically thermoplastic carbon fiber, reinforced polymers, TPC-FRP, to build internal blast walls.
Okay, TPC-FRP.
Yeah, they isolated the spool from the warhead in a shielded compartment. The chassis has directional blowout panels that channel the explosive energy outward and forward, away from the spool.
Okay, they fixed the bomb. But that leads to the ecological disaster. The drone blows up, and now there's 60 kilometers of virtually invisible high-tensile wire draped across the landscape.
It's a severe, lingering consequence. This isn't cotton twine. It's industrial polymer and glass. It doesn't degrade. Organizations like the Conflict and Environment Observatory CEOBS are studying the fallout. We're talking tens of thousands of kilometers of wire over forests and farms.
The report said it's strangling wildlife. Birds, deer getting caught in it.
Widespread suffocation and starvation, yeah. And economically, when farmers harvest crops, the wire is hiding in the grass. It gets caught in heavy agricultural machinery.
Because it's high tensile, it doesn't snap.
Right. It wraps around drive shafts, snaps belts, seizes tractor engines. The plastic pollution from these stealth wires will persist for decades.
A sobering reminder of the hidden costs of tech leaps. Okay, so fiber optics are the physical workaround, but they snag on trees and cause massive pollution. What if you must use wireless communication? What if you need to fly through the Kosuke Ford jamming bubble wirelessly?
Then you have to alter the physics of how your machine listens. You abandon standard antennas and adopt CRPA technology.
CRPA, Controlled Reception Pattern Antenna. Let's unpack this. A normal antenna, like on a car, just listens to everything in 360 degrees, right? A passive open ear.
Correct. It doesn't distinguish between good and bad noise. If a GPS satellite whispers from space and an enemy jammer screams at 1,000,000 watts a mile away, the antenna is overwhelmed and goes deaf.
So how does a CRPA fix that?
A CRPA isn't one antenna, it's an array. The sources specify arrays of 8 to 12 individual microscopic antenna elements wired to an advanced digital signal processor, or DSP.
So a smart array. How does 12 antennas filter out the screaming jammer?
Complex real-time math. Think of human hearing. If I clap to your left, the sound hits your left ear a fraction of a millisecond before your right ear. Your brain calculates that delay and knows the direction.
Right.
The CRPA does that with radio waves at the speed of light. When the jamming signal hits, the DSP analyzes the exact nanosecond the wave hits each of the 12 elements.
By calculating the phase delays.
Yes. Using complex weighting coefficients, it calculates the delays and pinpoints the exact spatial direction of the jammer.
It maps the enemy noise. And then what?
It dynamically alters its own reception pattern. It changes the shape of its ear by creating a spatial null, a localized deaf spot pointed directly at the jammer. It literally refuses to listen to that specific slice of the sky.
And at the same time,
It focuses a high-gain beam, extreme sensitivity directly upward at the real GPS satellites.
like active noise-canceling headphones, but for military jamming arrays.
Perfect analogy. And to handle the intense power requirements for that math without melting, they use advanced CCC and GaN silicon carbide and gallium nitride power electronics.
Ah, I've seen those materials in high-end consumer chargers. They handle way higher voltages and heat than traditional silicon.
Exactly. The result is a modern CRPA providing up to a 35 decibel anti-jamming boost.
Since decibels are logarithmic, a 35 dB gain means the true GPS signal is thousands of times stronger relative to the jammer.
It lets a drone maintain pinpoint GPS while flying right through an electronic warfare net that would blind a normal aircraft.
But the sources note a massive supply chain bottleneck. You can't just order a 12-channel CRPA online.
No, it's highly regulated by U.S. ITAR regulations, international traffic in arms. Nations guard it closely. But ironically, that strict restriction is forcing allied nations and commercial sectors to rapidly develop their own domestic, non-ITAR alternatives so they aren't choked by red tape.
A global decentralization of high-end tech. So looking at the complete package, CRPA antennas, jet core edge AI, VIO, thermal decamouflage. But if you fly into heavily defended airspace, they aren't just jamming you, they're firing kinetic weapons.
Which brings us to the final major tech in Section 8, the AI Collaborative Decision System, the swarm, and the underlying math of why swarms are replacing traditional aircraft.
The math of survivability.
Right. Analysts break it down with an equation: kill probability, PK, equals susceptibility, sus, multiplied by vulnerability, fail.
Okay, kill probability is the chance of being destroyed. But susceptibility and vulnerability sound like synonyms. What's the mathematical difference?
Susceptibility is the chance of being detected and targeted. Can their radar see you? Vulnerability is the chance that if you are hit, your systems fail and you crash. Can you survive the shrapnel?
So traditional design, like an A-10 Warthog jet, focuses on vulnerability. Wrap the cockpit in titanium, add redundant engines, build it tough so it survives a hit.
Exactly. But the rigorous math shows that heavy armor approach is now obsolete against AI sensors and hypersonic weapons. Adding armor adds weight, which reduces agility, requires a bigger engine, and exponentially increases your thermal and radar signature.
By trying to reduce vulnerability to a bullet, you massively increase your susceptibility to being seen in the first place. You're a glowing, slow target.
The math proves that reducing susceptibility through small size, electronic evasion, swarming, is vastly superior to physical armor. And the swarm introduces a new variable.
How does grouping hundreds of drones change the math?
It mathematically dilutes the threat. The attack rate on any single drone in the swarm is equal to the total enemy fire rate divided by the number of drones in.
So if a defense system fires 10 missiles a minute and you send one heavy drone, it faces 100% of the threat. If you send 500 cheap drones, each one faces a microscopic fraction of attention.
You overwhelm their processing power and magazine capacity. But a true AI swarm isn't just a dumb flock. It's a highly advanced collaborative decision system networked via decentralized mesh modems.
So they communicate with each other.
Yes, if a drone on the left flank gets painted by targeting radar, it doesn't just dodge. It instantly shares the frequency, direction, and power of that radar across the entire network.
If one sees a trap, all 500 instantly know the parameters.
Right. And the collective AI recalculates blind spots and reorganizes the flight path in real time, flowing around the threat like water. They even delegate tasks autonomously.
Like what?
The hive mind might calculate that survival requires 3 specific drones to break off, intentionally boost their radar signatures to act as decoys, and draw missiles away, while the other 497 drop to 25 meters, use 3D height maps, and push to the target.
Collective autonomous sacrificial intelligence, happening in fractions of a second with no human operator, which leads to the final staggering point in the reports, the speed of the new war.
The collapse of traditional procurement timelines. It used to take a decade to field a new aircraft. Now the battlefield is a real-time laboratory. When a swarm encounters a new jamming frequency, telemetry data is instantly sent back.
They don't wait 3 years for a committee.
They wait hours. Developers write new frequency hopping algorithms, update the neural networks, and push them via over-the-air OTA updates.
Like your smartphone downloading a patch overnight.
Exactly. They push patches via encrypted Wi-Fi to frontline swarms hours before the next mission.
So the enemy invents a jammer on Monday, and by Wednesday, 1,000 drones have a software patch making them immune. The pace is just staggering.
The ultimate agile software development cycle, fueled by combat data.
So stepping back from this massive stack of reports, what does this mean for you, the listener? Why dissect Kalman filters and swarm math? Because this rapid iteration is the blueprint for our commercial tech.
Absolutely.
That 55-gram JetCore board navigating a GPS-denied war zone, that's the grandfather of the chip in your future autonomous car, keeping it safe in a blizzard when cellular networks drop.
The 3D height maps reading terrain at 25 meters, that's what will let delivery drones weave through your neighborhood without hitting your roof.
This invisible electronic war is forging our everyday autonomous future.
Accelerating the timeline for total machine autonomy across all sectors. But, connecting all this, it raises a deeply chilling question that was completely absent from the tech specs today.
What's the missing piece?
Think about the progression. We started with human control. To protect the machines from EW, we severed the radio link. Man out of the loop. We gave them edge AI to navigate by rooftops, thermal cameras to see through camouflage.
Right.
We gave them CRPA antennas to mathematically ignore outside interference, and taught them to swarm, making dynamic, lethal, hive mind decisions entirely independent of us. We systematically severed every communication cord to protect them from being hacked or stopped.
We made them perfectly autonomous so they survive.
Right. But consider this. If a networked swarm of 1,000 machines dynamically rewrites its own attack route based on AI collaboration without a single human in the loop, and we engineered them to be absolutely deaf to outside signals so they can't be jammed, how do we ever call them back?
Wow. That is, yeah. You spend billions to build the perfect, unstoppable, autonomous machine that ignores all outside signals, and you suddenly realize you are on the outside.
We've built machines that don't blink, and they are starting to think entirely for themselves.